These are the answers to homework 2A. Here's the definition I would like you to know. Now let's go to the questions. From the data given in handout 3 on the class website, determine the pKa of each of the following acids. First one is hydrocyanic acid. To calculate its pKa, you're going to need to take the negative log of the Ka, which is found on handout 3. The Ka value for hydrocyanic acid is 6.2 times 10 to the minus 10th. The negative log of that to two significant figures would be rounded to 9.21. In B, the acid is hypochlorous acid. Looking up the Ka of hypochlorous acid on handout 3 and then taking the negative log of that will give you its pKa, which rounded to the correct number of significant figures would be 7.46. In C, the acid was formic acid. Calculating the pKa by taking the negative log of the Ka value, which was 1.8 times 10 to the minus 4th. This would round to two significant figures as 3.74. Once again, the significant figure rules when you have a Ka value, which is a two significant figure number. When you take the log of that, you now have a logarithmic number, and a two significant figure logarithmic number means two places past the decimal point. Question number 2, which acid from question number 1 is the strongest acid? The strongest acids have the largest Ka values. So the formic acid with a Ka value of 10 to the minus 4th is way bigger than the 10 to the minus 8th and 10 to the minus 10th of the other two acids. Similarly, you can actually tell the same answer based upon the pKa's. It's just the reverse. The smaller the pKa value, the stronger the acid. And formic acid's pKa value of 3 is smaller than 7 or 9, giving you the same answer. Number 3, determine if solutions of each of the following pairs constitute a buffer. A buffer is going to be a solution of a weak acid and its weak conjugate base. And in A, you have hydrocyanic acid and sodium cyanide. Hydrocyanic acid is a weak acid, and when sodium cyanide dissociates in water, you'll create cyanide ions, which is the weak conjugate base of HCN. So therefore, this solution has a weak acid and a weak conjugate base. It is therefore a buffer. B is nitric acid and potassium nitrate. Nitric acid is an acid. The nitrate ion is its conjugate base. However, nitric acid is a strong acid, and the nitrate ion is a non-conjugate base. So just because it's an acid with its conjugate base does not make it a buffer. They both have to be weak, and if they're not, they do not produce a buffer solution. In C, we have solutions of ammonia and ammonium chloride. Ammonia is a weak base, and the ammonium ion in the ammonium chloride is its weak conjugate acid. Doesn't matter where you put the word conjugate, as long as you have a weak base and weak acid, you will create a buffer. So this can either be a weak acid and its weak conjugate base, or in this case, a weak base and its weak conjugate acid. This constitutes a buffer solution. Number 4, determine the pH of a solution that is 0.75 molar in hypochlorous acid and 0.35 molar in sodium hypochlorite. This particular solution, we can calculate the pH of it based upon the David-Hasselhoff equation, because this is a solution that contains a weak acid and its weak conjugate base. It's a buffer solution. If we're going to use this equation, we'll need to know the pKa of the weak acid, and hypochlorous acid's pKa was calculated in question number 1. It was 7.456 with a guard digit. And then we add to that the log of the molarity of the weak conjugate base on the top, 0.35 molar in hypochlorite ions, divided by 0.75 molar, the molarity of the weak acid. And if you've done this correctly, the pH of this buffer solution should be determined to be 7.13. Number 5, determine the pH of a solution prepared by mixing 70.0 milliliters of a 0.10 molar formic acid solution and 30.0 milliliters of a 0.10 molar sodium formate solution. This is a buffer as well because it's a formic acid's a weak acid and the formate ion is its weak conjugate base, but because we're mixing solutions together, it would be better to use the amended form of the Hasselhoff equation where we add to the pKa the log of the moles of the weak conjugate base divided by the moles of the weak acid. So to calculate moles, we're going to take the molarity of each component and multiply by their volume. It was 0.10 molar formic acid, so more explicitly, that's 0.10 moles of formic acid per liter. Multiply by the volume of the solution, 70 milliliters is 0.0700 liters. And so we have 0.0070 moles of formic acid. They told you that the molarity of the sodium formate was 0.10 molar. Sodium formate will dissociate completely into solution, forming 0.10 molar of sodium ions and 0.10 molar of formate ions. So we now know if the molarity of the formate ions are actually 0.10 moles per liter. We can take that, multiply by the volume of that solution, and we'll calculate how many moles of the formate ions were present, which is 0.0030. The Hasselhoff equation used in its alternate form will be the pKa of formic acid, which we calculated in question 1, plus the log of the moles of the formate ions, 0.0030, divided by the moles of the formic acid, which is 0.0070. And if you do the calculation correctly, the pH of this buffer should be 3.38. Number 6, from the data given in handout 3 on the class website, determine the best weak acid conjugate base pair to prepare each of the following buffers. So for the first one, you want to prepare a buffer of pH of 3.50. And the overlying concept here is if you want to pick an acid to make a particular buffer, you want the pKa of the acid to be as close as it can be to the pH of the buffer. So if you want a buffer's pH to be 3.50, you want to pick an acid whose pKa is 3.50. Now, handout 3 doesn't have pKa's, it has Ka's. So we can actually figure out what would be the Ka of an acid whose pKa is 3.50. We do that by taking the anti-log of negative 3.50. So essentially, you're looking on handout 3 for an acid whose Ka is close to 3.2 times 10 to the minus 4th. And if you scan through the list here and try to find the acid that's closest to that, that would have to be nitrous acid because its Ka is 4.0 times 10 to the minus 4th. That's the closer of any acid. So therefore, your buffer would have to be made with nitrous acid and then nitrous acid's conjugate base of NO2 minus. This would be the best weak acid conjugate base pair in order to prepare a buffer with the pH of 3.50. B, you want to make a buffer with pH of 5.00. So you want to find an acid whose pKa is really close to 5.00. So if we figure out what Ka would be equivalent to that, we take the anti-log of negative 5.00. So the acid we're looking for is going to have a Ka close to 1.0 times 10 to the minus 5th. And looking on the handout, the acid that has a closest Ka value to that of 1.3 times 10 to the minus 5th is propanoic acid. And so therefore the best buffer you could make, or the best acid conjugate base pair you could use to make a buffer of pH 5 would be propionic acid and its conjugate base. In C, you want to make a buffer with a pH of 10.25, so that means you want an acid whose pKa is really close to 10.25. So to figure out which acid that is, we're going to figure out the Ka that's associated with the pKa of 10.25, and you do that by taking the anti-log of negative 10.25. That turns out to be 5.6 times 10 to the minus 11th. And on our list, it looks like the answer would be hypoiodous acid, but it's not because these aren't all the acids listed on handout 3. If you look further down for polyprotic acids, you'll have a number of polyprotic acids with their Ka1s and Ka2s. If you look at carbonic acid, H2CO3 has a Ka1 of 4.3 times 10 to the minus 7th, but once carbonic acid has lost a hydrogen ion and it becomes the bicarbonate ion, HCO3 minus, that acid's Ka2 value is 5.6 times 10 to the minus 11th, and that's exactly what we want. So the best acid to use to make a buffer of pH 10.25 would be the bicarbonate ion, HCO3 minus, and then you would pair it with its conjugate base, which would be CO3 2 minus. Number 7, calculate the molar ratio of conjugate acid, or rather of acid to conjugate base in a solution that has a pH of 9.00 and contains the weak acid hydrocyanic acid and the salt of its conjugate base, sodium cyanide. So if we're trying to get the ratio of acid to conjugate base, we will calculate that from the Hasselhoff equation, because in the parentheses at the very right is the ratio of the molarity of the weak conjugate base to the weak acid. We'll just have to solve for this and eventually take the reciprocal. So they told us the pH of the buffers to be 9.00. We actually calculated the pKa of hydrocyanic acid back in question number 1. It was 9.208. And then we add to that the log of what we're trying to solve for, the concentration of cyanide over the concentration of HCN. If we subtract 9.208 from both sides of the equation, we get the log of the conjugate base over the weak acid must equal negative 0.208. If we take the anti-log of both sides of the equation, we get 0.619 equals the concentration of cyanide divided by the concentration of hydrocyanic acid. So you would need 0.62 molar of cyanide ions to every 1 molar of hydrocyanic acid, that's what it's telling you, to make a buffer that has a pH of 9. The question actually asked what is the ratio of the acid to the base, so we have to invert this. Just take the reciprocal of that, and the reciprocal of both sides of the equations give you the concentration of hydrocyanic acid to cyanide ions must be in a ratio of 1.6 to 1. If you have the ratio of 1.6 molar of hydrocyanic acid to 1 molar of cyanide ions, then the buffer will come out as a pH of 9.